Hello and welcome back. This is presentation 7.1, part of a multi-part series in statistics. The topic is the Central Limit Theorem, which forms the foundations of inferential statistics. We want to bring to your attention the development team, Brad, Spencer, and Amanda. And we want to look at the statement of the Central Limit Theorem, starting with a random variable x, which may denote the stats 251 marks in a very large population at a university perhaps. It's normally distributed with a mean of 70 and standard deviation 10. 60% of the time a single x value, or the probability that a single x value will fall within one standard deviation, or plus or minus 10, of the mean of 70 is 68%. Those values are 60 to 70 to 80. Now we're going to take random samples of size 25, and you can see here that when you take a random sample, the sample, if it's truly random, should fall around 70. And watch these come on the screen here now. These are just simulations. So they build up around 70, and we're saying that they really form a normal distribution. And the center of that distribution will be at 70. We say mu sub x bar, that's the mean of the x bars, will be the same as mu of x, which will be 70. And the standard deviation will be sigma over square root of n, much smaller of course, and that will be 2.0. So looking at the diagram here, 68% of the time x bars will fall within plus or minus 2 units of 70, giving a range of 60 to 72. With 68% probability, or 2/3 the time, and that as your sample size increases, that the estimates become more and more exact, and sigma sub x bar will go towards 0. Now we've gone into Excel here, Microsoft Excel, and did a simulation. We've generated 1,000 numbers here, and we're looking at the first 25, and as you can see here, the sample means based on n equal 25. Notice how they fluctuate around 70. Now there's 100 sample means here. The average of those sample means, or the mean of the means, is 70.12. Standard deviation is 2.08. We want to compare these with the theoretical values of 70 and 2.0, and you can see they're very, very close here. 95% of the time, 95% z equal plus or minus 1.96 times the standard deviation gives you a region in which 95% of the x bars will fall between 66.08 and 73.92. Now we're going to look at a distribution of sample means for n equal to 100, and these down here represents the first 100 data items in each column, and notice there's 100 of them, and we're saying the average of these means, or the mean of the means, 70.09, standard deviation 1.01, and comparing that to the theoretical values, we find that 95% of the time x bar will be found between the interval 68.04 and 71.96. 95% of the time, the x bars will be found between 68.04 and 71.96. Now we're going to apply that to the case where we're looking at the population, the length of pregnancies, which are normally distributed with a mean of 268 days, standard deviation of 15 days. We want to find the probability that one pregnant woman is selected at random, find the probability that her length of pregnancy is below 260 days. So step 1, find the x is 260, and notice standard deviation 15. Find the z-score, minus 5.533. Go to your table, and that value there is, we've estimated the 29.7%. 0.2971, and that becomes our answer. Almost 30% chance that a single woman selected totally at random, the probability that her length of pregnancy will be below 260 days. Now we're going to look at a sample of 25 women. We find that for the case of n equal 25, down here in the lower right, sigma sub x bar is sigma over square root of n, or 3. This means that if x bar is 260, notice we're working with x bars now, the z-score is 260 minus 268 divided by the standard error of 3. That's the z-score is minus 2.67, and the probability is 0.0038 or 0.004. 4 in 1,000 chances of this happening. Very rare event. So that if we found that these women were put on a special diet before they became pregnant, then this would suggest that there's cause for concern here. Medical officials should be concerned, or should be involved. Well, that's the end of presentation 7.1. We ask you to review it once more and go to presentation 7.2. Thanks for watching.